Good, how are you?
Not bad. So they're going to come over with the mic.
Yeah.
Now this is a different kit than we had the other time, so the microphone doesn't project to the room. It only goes to our recording system.
So I will use this one?
You have to use this
I
one.
was using it last time anyway.
You have to use both.
Anyway, so I'm making a necklace of microphones.
All right. I think the kit that you had the last time, it's one of the newer kits, and it can broadcast to the room at the same time, so you don't have to use two.
Right.
I'll confirm that.
Okay.
But this one's an
Doesn't
older
matter.
kit. So.
Once I put it around my neck, I forget about them.
Great. So you can just log in and start Desktop Presenter.
Okay.
You're going to use that a bit, right? Or
Yeah,
no?
I'll start with this, but yeah, you're right. I actually don't want them to see mine.
Yeah, 'cause we don't want to do this in the middle of the recording.
I didn't have time to complete the instructions.
All right. So,
I had 3 hours yesterday.
all right. Guys? David? They should be bringing you a mic now. All right, so Desktop Presenter is just, you can look for it, just go that, and then Desktop, you see it's this one right there.
Okay, so click on that.
Yeah, the yellow one. Not happy? An arrow up to.
Still, I'm going to need them on.
Is it working?
Oh, okay, it's showing some signs of life.
Yeah. All right.
So I don't touch it. Okay.
That's it. Yeah.
Good. I just want to give them. Yeah. Okay.
You'll be using.
Okay.
Do you want to set it up or myself, or do you want me to help you?
Let me see. Maybe I'll manage. You actually use this.
Probably like here, like here.
Okay.
Yeah, it's good enough.
I'll put in the teapot.
Yeah, just clip it. That's it. I think maybe you clip over here is more stable, like in the middle. Yeah, that's a good one. Good position.
Thanks.
All done.
Thank you. Now, could you please try to answer this question while I'm strung with my chains and leashes and everything? Okay, good morning once again. Do you know the answer to this question? So if f of x equals 5 and the operating point x naught is 1, what will be the linearized expression for f of x? If you still don't know, let's try step by step. Let's use the equation for linearization. We need fx of naught plus brackets x minus x naught df of x by dt at the operating point when the derivative equals to x, the x equals to x naught, the value of the derivative. So when x equals to 1, the value f of x will be 5 anyway. So it is 5. Plus x minus x naught is 1. And then the derivative of f of x will be 0 because f of x is constant. So f of x would be 5. So linearized f of x somehow is the same as non-linearized f of x. Is that normal? Yes. Yes, it is. Because if the function is a straight line, no matter where the operating point is, the tangent to that straight line will be the very same straight line. So what we did here is not wrong, but it was a little bit of a waste of time. We were linearizing something which was already linear. Okay. So if you're not sure that something is linear, of course, by all means, do this. Make sure you're right. But otherwise, when you see a straight line, no need to linearize it. And it's not only this one, where f equals to constant. Any straight line like this, try to linear no matter where the operating point may be. When you draw a tangent to a straight line, you will get the very same straight line. Okay. So linearization doesn't necessarily have to be something scary or something difficult. Sorry, yeah. Sorry? The x, thank you, not the x. Very good, thank you. Yeah. Right, okay, so this is my good morning question. I always start lectures with a question. I hope to warm you up that way. Now we can continue with lecture 2. However, you know, I didn't fully answer all your questions last time, so I would like to answer them. Actually, before that, I'm going to explain what will be happening in the second hour. I said there will be a tutorial, interactive tutorial, where you will take the tutorial set from the Moodle and work on those problems, sets 1 and 2, today. And I and other demonstrators will come and we will help you as soon as you ask us for help. So any question. All I'm going to ask you is to free every third row so we can walk and reach every single one of you. When you have a question, we don't have to climb over 5 other students to reach you. So free after this class, obviously not now. Free every third row and apart from that. But there are not many of you today, so reaching everyone is not a problem. As I said, feel free, don't be shy, don't be embarrassed to ask questions. Any question is a valid question. And we are here to help you. Okay, now back to lectures, lecture notes. Okay, first there was a confusion about the meaning of this line here. So what you saw last time was an equal sign here, which ruined everything. But actually, there should be no equal sign, should be times. As someone suggested, the previous equation was multiplied by theta naught squared. However, that was not necessary. So now this line is correct, but it is a little bit redundant, because you can really jump straight from this line to the final linearized expression. So just for the sake of accuracy, I corrected this line, but yeah, maybe it shouldn't be there though. The other thing someone pointed out very correctly, with these boundary values substituted, we were talking about derivatives here, okay? So how did we get minus f of 0? We said that this function, this expression here, when we substitute infinity, time equal infinity, we get e to the minus infinity will be 0, and f of, and then we said 0 times anything will be 0, okay? So we ignore that part. So for the lower boundary, then we have e to minus 0 is 1, and then we have f of 0. So one of you then expressed a doubt that the first assumption that the whole expression will be 0 when time is infinity may not be always true if f of t grows to infinity faster than exponential going, approaching 0. So this is an assumption we make for Laplace transform. So Laplace transform works under that assumption, that exponential function e to the minus st approaches 0 faster than any f of t may approach infinity. Okay. And after all, if you think about it, 0 is much closer, infinity is too far. So it's much easier to get to 0 than to infinity. And I think that's all I had in terms of what was not done, what was not completed last time. So we stopped with these shift theorems. Okay, so I repeat once again. The shift theorem in the S domain states that, or S domain shift, complex domain shift. If a function of time, in the time domain, a function can be rewritten such that you have an exponential term multiplying the rest of the function, then you can easily find the Laplace transform by finding the Laplace transform only of the function without the exponential term. So ignoring the exponential, find the Laplace transform f of t. That will be f of s. And then check the coefficient multiplying t in the exponential function. And that coefficient, opposite sign of that coefficient, will give you the shift. So instead of s, you write s plus a everywhere in that function f of s. And then we had an example. So if you are looking for a Laplace transform of this function, so exponential times sinusoidal, first you ignore the exponential and only find the Laplace transform of the sine function. And at that time, I didn't have tables ready. So if you look for a sine function, Laplace transform of sine omega t will be, this mouse is fine, equal to omega over s squared plus omega squared. So you have omega over s squared plus omega squared. However, s has to be shifted by b. So instead of s squared, you have s plus b squared. Right, so that's how you can make your Laplace transform simpler. Initially ignore exponential, then shift s, but whatever is multiplying t in the exponential. Having said that, you have that function over here. That example in the tables a bit later on. So case 20, that shows exactly that. Fine. Now, time domain shift looks very similar, just opposite. So if in the S domain you have an exponential term multiplying any function, then you can try to find the inverse Laplace of f of s, ignoring the exponential, and you get f of t. Then you take the coefficient in the exponential function and shift t by that much, apart from, in this case, it's minus a. And a little detail here, you also have to multiply by the step function, u of t, by u of t also shifted by a. Also shifted by a seconds. Now, what this u of t minus a is shown here in this diagram. So u of t will be 0 until time equals to 0, and that it will jump to 1 and stay 1 until infinity. U of t minus a means that this function equals to 0 until time equals to a. And then it jumps to 1 and becomes 1 until infinity. Okay. Once again, u of t equals to 0 for time less than 0 equals to 1 for time greater than 0. Okay. Now, instead of t, you have t minus a. So when this argument equals to 0 or less, the whole function equals to 0. When is t minus a equal to 0? Where t equals to a. So a is that critical point. Okay. These shift theorems, especially the time domain shift theorem, can help us decompose some complex forms. Some complicated, by complex, I don't mean those that have I in it, so complicated, let's say, forms. So this function here, they like to call a duty cycle. It looks like a duty, some machinery that is first warming up, then has to be switched off temporarily to cool down, and maybe later on you will have another function like that, but focusing on only one. So how do you find a Laplace transform of a function like this? You can break it into individual functions. You break it into those functions whose Laplace transforms are easy to find, or whose Laplace transforms you already know. So this function can be broken into this ramp function. But this ramp function simply keeps growing all the time to infinity. So after b seconds, you apply this negative ramp with the same gradient, just negative. And this negative ramp will stop the growth. So when you combine this ramp with this ramp, you get this, and then a constant. Okay? Because this second ramp does not exist before time equals to b. It starts here. And then to destroy this constant, you need to apply a negative step that will offset that constant. So you end up with 0. So these three combined will give you the original function. Now, you can find Laplace transforms of each individual function. The first ramp should be easy, because this ramp exists from 0 to infinity. And we know from the last class that a Laplace transform of a ramp or unit ramp is 1 over s squared. This is not a unit ramp. The slope is a over b. So therefore, it's a over b s squared. The second ramp, first of all, has a negative gradient, minus a over b. First. Second, it does not start until time equals to b. So it is minus a over b s squared, but because of the shift by capital B, you multiply by e to the minus bs. You apply this. And finally, the third function is a negative step, shifted also by b. So it is a negative. It is a step, 1 over s. The magnitude of the step is a. And don't forget the time delay, the time shift by b. So this would be the Laplace transform of this particular function, of this particular waveform. Okay. Once again, these two expressions for both s domain shift and time domain shift will be, so those equations will be given in your exam sheets. Okay, partial fractions. A very important rule of a Laplace transform is this. So Laplace transform of a sum of a function, each function multiplied by a constant, can be rewritten as this. First constant times Laplace transform of the first function plus second constant times Laplace transform of the second function. So this is a property of a linear operation. And Laplace transform is a linear operation because it is effectively an integral. So when you integrate a function, you can always take the constant out of the integral and then integrate whatever is left. Also, when you have integral of a sum of two functions, you can integrate them separately and add them together. And Laplace transform by its nature is an integral, so this is true. That means that if you have an S-domain function which is too complicated to be found in the tables, what you can do is try to break that function into a number of simpler functions whose transforms exist in the tables. Now you will see, I don't know whether you check the tables, but pretty much all functions in the S-domain are in this form. So you have a polynomial in the numerator divided by a polynomial in the denominator. The first rule you should apply is to factorize the denominator as much as you can. And if you do it properly, you're going to end up with either first or second order polynomials in the denominator, a product of first order, second order polynomials. Okay. If it is a third order polynomial, it must have at least one real root, so you can factorize down to one first, one second order. If all three roots are real, then you have three first order polynomials. Hope we all know that. So in this case, you can rewrite this n of s over d of s, your big, clumsy, chunky S-domain function, and rewrite it in this format. A over s plus d1, b over s plus d2, assuming d1 and d2 are real roots of the denominator. And then if you have a case with a pair of complex conjugate roots, then you have to leave the second order here, s squared plus d3, s plus d4. But what you have in the numerator here has to be a polynomial of the first order, n minus 1, n minus first order polynomial, cs plus d. In case the same root is repeated more than once, so if you have s plus 3 squared, so the root minus 3 is repeated twice, or it can be repeated many times, then you have to take that root into account as many times as it is being repeated, every time with an increase in the power in the denominator by 1. So it would be, if a root is repeated n times, then you have to write a1 over s plus d plus a2 over s plus d squared, plus and so on until you reach n. an over s plus d1 to the power of n. And these are all rules you need to know about partial fractions. Now we are going to do a number of examples, because there is very little theory here. So let's practice some partial fractions. So if f of s is given in this form, the numerator is s plus 3, the denominator is s squared plus 3s plus 2. Find the partial fraction. First thing, factorize the denominator. Very basic thing. When you try to factorize, you see that this polynomial has two real roots. So let's rewrite it as s plus 2, s plus 1. Then rewrite the whole function as a over s plus 2 plus b over s plus 1. The term on the right-hand side now needs to be joined into a single fraction. So left-hand side is f of s, which is this part. On the right-hand side, you have a times s plus 1 plus b times s plus 2, all divided by s plus 2 and s plus 1, because, yeah, that's how you add two fractions together. I still hope this is trivial to you. So now you have left-hand side, right-hand side. The denominators are the same. That's fine. That means that the numerators have to be the same as well. So you end up having s plus 3 being equal to a s plus 1 plus b s plus 2. Your task is to find a and b, because you want to get this expression right. So you don't know a, you don't know b. The safest way is to equate the coefficients. So the coefficients with s on this side is 1. On this side, you will have a plus b. Then coefficients with s to the power 0. On this side, you have 3. On this side, you will have a plus 2b. Or, if you're happier with the shortcut, I'm showing you the shortcut here. So you can first say s equals to minus 1. So if I take s to be equal to minus 1, I'm going to lose this term here. So I can easily find what b equals to. S is minus 1, so I have 2. Minus 1 plus 3 is 2. B times minus 1 plus 2 is 1, which is b. So b equals to 2. Then next step, I have s equal to minus 2. So I will lose this term because it's 0. Now, minus 2 plus 3 is 1. A times s, which is minus 2 plus 1, which is minus 1. 1 equals minus a, or a equals to minus 1. So if b is equal to 2, then I have 2 over s plus 1. A equals to minus 1, so I have minus 1 over s plus 2. That's partial fractions. Inverse Laplace transform of this function can be now easily found in the tables. So we are looking for the s plus 1 in the denominator. Or s plus a. It doesn't have to be 1. It can be any constant. And here it is. 1 over s plus a. Inverse Laplace is e to the minus at, where a, in our case, would be equal to, well, in this case is 1. In this case is 2. So 2 stays unchanged. 1 over s plus 1 will give us e to the minus t. Then minus, this is e to the minus 2t because of 2 here, okay? And then you multiply everything by u of t. Yeah, okay. I have to and you don't have to. Okay, that's actually a good question. I'm multiplying by u of t because it is, if I want to be mathematically rigorous, this is the way to do it. You multiply u of t. I can't afford, because if I don't make something inaccurate, someone in this room will find out and say, oh, wait a minute, this is not correct, as was the case last time. But actually, if you forget to do it in your exam, no problem. It won't be regarded as a problem. I'll actually show you. That's a good question. And deserves a little bit more attention. So if you have a function in time, so in the time domain, okay, any function. And now you're applying Laplace transform. So in the S domain, f of s. In the S domain, when you apply the Laplace transform, you get something completely different. Okay, so this is your new function in the S domain. So here you are doing Laplace transform. Now, if you want to go back, so inverse Laplace. You want to go back into time domain. You won't get the same function. What you're going to get is only this part, the positive part of the original function. So if I can now reproduce this, that will be the same. But this part, the negative part, will be lost. Why? Because this thing here is an integral from 0 to infinity. Laplace transform integrates from 0 to infinity. So Laplace transform doesn't care what the function was like before time was equal to 0. It kills that information. So during the Laplace transformation, this information is lost. So when you're trying to recover your time domain function, you don't have that information. So your function actually looks like this, which is equivalent to multiplying f of t by u of t. Because when you multiply by u of t, you're multiplying by 0 in this range and multiplying by 1 in this range, which gives the same thing. So strictly speaking, inverse Laplace transform gives you this, doesn't give you the rest. And that's why I'm writing u of t. But again, it won't be held against you if you forget to write u of t. Any questions while the camera is on before we move back? Okay, so you will see in all my solutions u of t. If you don't, yeah, please yell, call foul, because it should be there. Having said that, I just have to warn you, don't take me wrong. If you are dealing with a shift, so u of t minus a, so shifted step function cannot be omitted. That will be regarded as an error in your exam. So when you're doing with the shift in the time domain, you have to show that shift. But u of t itself, you don't have to bother yourself. Although I believe now that I explained this, you will all write u of t anyway. Okay. Next example, slightly more complicated because now you have a third order polynomial in the denominator. You also have first order polynomial in the numerator. The first thing to check, is the denominator factorized? Yes, it is. So it is already factorized, but we need to rewrite it as a sum of 3 fractions. A over s plus b over s plus 2 plus c over s plus 4. Joining those 3 into a single fraction, the denominator will be a product of the 3 denominators. Numerator, a times the other 2 denominators, s plus 2, s plus 4, b times s, s plus 4, c times s, s plus 2. Equate the numerators as before. This is what we'll have. You need a, b, and c. When you make s equal to 0, this term will disappear and this term will disappear. So you'll be able to find a. If f is 0, you have 2 times 6, which is 12. Here you have 2 times 4 times a. So a will be equal to 12 over 8, which is 1.5. Repeat the same for the other 2 roots. S equal to minus 2, you are going to lose wherever s plus 2 is. So this will be 0, and this will be 0. So that's how you find the value of b. And finally, make s equal to minus 4, you're losing the first two terms, so you find the value of C. Okay, so A is 1.5, B is minus 2, and C is 0.5. Okay, so now we know the value of A, it's 1.5. 1.5 over S in the time domain would be 1 over S would be U of t. 1 over S is a unit step function. Just the magnitude of the step is not 1, it's A, so we have 1.5 S. B is minus 2, so we have minus 2 here, or S plus 2. Something over S plus 2 is an exponential function. Okay? Check the tables. S plus 4, another exponential function. So I'll leave that to you to finish, to really write down f of t. Next example, unless you have a question. Oh, yes, sir. Correct. Yeah.
Then when you were doing what you did before, where you times the whole thing by u of t, would you put all of that f of t in brackets then u of t by everything, including the thing which is already
Either is correct. Either is correct. You know why? Because multiplying u of if you square u of t, you are still getting u of t. So it doesn't matter how many times you multiply u of t by u of t. Because 0 squared is 0, 1 squared is 1. Or 0 to any power. So you can do it either way. Put u of t in brackets plus exponential, everything times u of t. Or you can put 1 plus exponential, everything times u of t. It's the same. It's OK. Other questions? Good. OK. Example number 3 is interesting for a few reasons. First of all, it is another example of partial fractions. Second, introduces some very interesting terminology that you should become familiar with. What is the unit step response from a system where the transfer function is? So the transfer function is given as a function of S. They want us to find the unit step response. What is that? How do you understand that? You don't. OK. How do you understand response of a system? I can hear some murmur, but I can't understand. OK, yeah. I would say output. So you have remember how we define the system, how we describe the system. Input, output. So the response of the system is the output when you apply certain input. That's what the response is. That's how the system, you apply an input and the system responds. So yeah, it is the output. But unit step response, that means that the input is a unit step function. So you want to see how the system responds when you apply unit step, what kind of function you have as the output. That is the question. The translation to plain English of this question is, find the output if the input is a unit step function. Right. And now you have the transfer function. Last time we explained what the transfer function was. Okay, it is actually a description of the system in the S domain. But the definition of transfer function is output over input in the S domain, once again. Okay, so here it is. So this is the definition. The transfer function is output over input in the S domain. So we know the input. It is a unit step function. We want to find the response, the output. So VO will be equal to the product between the transfer function and the input. Before we do anything, just a piece of warning. In your tables, all functions on the right-hand side are in the normalized form. And by normalized, we mean that the coefficient of the highest order of the denominator. Okay, if you look at all these denominators, the coefficients with the highest order term is always 1. S times S, S times S. Okay, S times S times S. So the higher order coefficient is always 1. That means the function is written in the normalized form. If you don't if your function you are dealing with is not normalized, then you can't apply this table. You can't directly apply this table. So you always have to normalize your function. Again, S times S squared. S squared times S squared. So the highest order, S squared times S squared, it's always 1. The highest order coefficient is always 1. So in this case, you don't have that. You have 0.2 multiplying S. So you have to get rid of that. So you have to multiply by 5 both the denominator and the numerator to get rid of 0.2. So when you do that, you get 25 times 1, which is 25, and 25 plus 0.4 is 10. So you have 10s plus 25. In the denominator, s plus 1 doesn't change, but 0.2 plus 1, when multiplied by 5, gives you s plus 5. So now you have a normalized transfer function. Now you can multiply this transfer function with the input function, which is 1 over s. So the output VO equals transfer function times input, all in the S domain. So it's 10s plus 25 over s times s plus 1 times s plus 5. Now we can apply Laplace transform. Now we can apply partial fractions before we get inverse Laplace transform of this. Okay, so the first root is 0, so we have a over s plus b over s plus 1 plus c over s plus 5. The denominators will be the same. Equating the numerators will give us 10s plus 25 equals a s plus 1 s plus 5 plus b s s plus 5 plus c s s plus 1, adding together 3 fractions. Again, we are still able to use the same trick, so we don't really have to equate the coefficients with all s terms. So when s is 0, we lose these 2 terms, so we get the value of a to be 5. When s is minus 1, we lose the first and the last, so we get the value of b. B is minus 3.75. And finally, we substitute s with minus 5, and we get the value of c to be minus 1.25. Okay. Here is our output in the S domain. To find the response in the time domain, we need to apply inverse Laplace transform. And that should be simple because we have tables. 1 over s is u of t. 5 over s is 5 times u of t. That's simple. That's the very top case. Again, nothing to memorize. It's here. The other 2 are exponential functions. 1 over s plus 1, again, will give us e to the minus t. So it's e to the minus t. The coefficient is unchanged, minus 3.75. And here, it is 1 over s plus 5, the same function, just e to the minus 5t. E to the minus 5t, the coefficient is unchanged, minus 1.25. So the response, I don't know if you want to sketch it at the moment, but the response will be first a step function and then 2 decaying exponential functions. So that's how this system responds to a unit step input. Okay, any questions on this? Right, the last example before we start our tutorial class. think I'm going to introduce a rule. If you're going to sit in any of these two rows, your task will be to remind me about the air conditioning as soon as I come into the theater. Because by the time we feel the heat, it's a bit too late. Anyway, it's running now. The last example for today, obviously we have a few more. Calculate the response to a decaying exponential input, e to the minus t. Decaying because that's exponential decaying, going to 0, approaching 0. Of a system whose transfer function is, and it's given here, 3s squared plus 9s plus 18 divided by s plus 4, s plus 5. So calculate the response. In other words, find the output to a given input. Input is e to the minus t. First, we need to know is what is the form of the input in the S-domain. So we need to find Laplace transform of e to the minus t. Laplace transform of e to the minus t is a case from the tables. It's 1 over s plus 1. Now, output in the S-domain will be the same as the product of the transfer function and the input. So now, yeah, this is the transfer function. Output VO of s is the same as transfer function. You will just have s plus 1 added here in the denominator. So you have a product of 3 first-order polynomials in the denominator. And the rest is pretty much the same as before. So break this function into 3 fractions. Into a over s plus 1 plus b over s plus 2 plus c over s plus 2, exactly the same as before. Combine those 3 now back together. And then in the numerator, you're going to have this long expression with a, b, and c. And you want to find a, b, and c. Applying the same procedure as before, you will find a to be 10, b to be equal to minus 1, c equal to minus 6. So v, O is missing here as a subscript. VO of s now becomes equal 10 over s plus 1 minus 1 s plus 4 minus 6 s plus 2. Here we have 3 exponential functions. So applying inverse Laplace transform tables, s plus 1 will give us e to the minus 1. S plus 4 will give us e to the minus 4 t. And s plus 2 will give us e to the minus 2t. Coefficients, let's not forget them. And everything multiplied by u of t. Any questions? OK, if not, then just please free every third row so we can run tutorials for the next hour. Interactive tutorials. You can start working straight away. You can take a short break. I won't take any breaks. I'm happy to answer your questions. That's it. Fine.
On that last slide you just did,
Yeah, sorry. Let's just get the sound off. So if it is down, we don't want people to hear. Okay, this one. Yeah.
okay, thank you.
Thank you.
Okay.
Yeah, I'll get the slide back. Okay. Here.
Yeah. Where does this UFT come from? I couldn't see it on the table.
Are you late for this one?
No.
I explained. This is how I explain it. Okay. This is your original function.
Yeah.
Any function. When you do Laplace transform is an integral from 0 to infinity of e to the minus st, blah, blah, blah.
Yeah.
Okay. That means that Laplace transform is not interested in this half of the function when time is less than 0.
Yeah.
Okay? So that one, that information is lost when you do Laplace transform. So you get into the S-domain, you get some completely different function. If you want to take the very same function back into the time domain, you won't get this. You will get this. Because this information does not exist here anymore. So you only recover this part. And the rest is 0. and then it jumps to whatever value you have here. This is equivalent to multiplying this by u of t. So that's why I said f of t, u of t. Because when you multiply u of t, you make this 0, and then the rest is multiplied by 1.
Sure. So on the, do you have the Laplace tables there?
Yeah.
What I was more confused by is, so this, so this one here,
They don't
they
have.
know the unit, they have the UT,
That's right.
but doesn't have.
Oh, okay. The tables are actually doing this. They are doing Laplace transform. They are not doing inverse Laplace. But because of that, if you're in the heat, of the exam and the stress of finishing the question on time, whatever, you read this, you write this, and you forget your key. You won't be penalized. That's why, because the tables don't have them, because these are Laplace from tables, not inverse Laplace.
So if you were going from that to that, you have to UT times UT.
Well, that's what that guy asked. That's the
Sorry,
same.
I was struggling to understand.
Because u of t times u of t is the same as 0 times 0 and 1 times 1. Yeah, no problem. Look. Any question on this?
Right.
Okay.
So I just want to know how to solve this problem. So if you would say that, like, in the negative domains, it will lose.
No, I said if this is f of t,
Yeah.
then this is f of t times u of t.
Yeah.
Because u of t, multiply u of t means here you multiply by 0, here you multiply by 1.
Yeah.
And that's why you have u of t. That's my answer to the question, why do I have u of t?
So that means u of t is kind of
Error in this function.
No, if you write u of t, then you're just writing it accurately. This inverse Laplace transform only gives you this, doesn't give you the rest of the function.
But how about if I want to get the rest?
You
So
can't.
what's it?
You
I
can't.
can't.
That information is lost. That's the nature of the Laplace transform. You can call it error. That's what Laplace transform does.
So that's the weakness of the Laplace transform.
You
Then
can call it
you
weakness.
always-
You can call it weakness. But why it is still useful is because we engineers, I'm interested what happens when I press the buttons. I'm not interested what was going on before the system started working. That's why. That's why it is a good tool for engineers. Mathematicians may say, oh, well, I lost that information. But I don't need it. I start the car, and then I'm interested how the engine is running, not how the engine is running before it's running. Guys, we'll be coming to answer those questions, but yeah, that's okay. If these theoretical questions, yeah, that's okay.
just wondering why do we use Laplace transform solving this?
Sorry?
Why do we use Laplace transform to solve this?
Yeah, the question is, what is the Laplace transform of this function? It's the opposite, not why are we using it. The question is, we want Laplace transform of this. So what we do, we break it into these three functions, and then we Laplace each function separately.
And so we simply treat a and b as a number.
Sorry? A.
Say a is 1 and b is...
Well, no, A is a constant, B is a constant. They're constant.
So,
I just have to,
I got one last question.
yeah,
Is it
we
okay?
have to police this theater a little bit because we said every third row should be empty. Sorry, guys. Yeah, they're still. Yeah.
Because I still can't understand why this one and this one and this one can be.
Okay. Just
Because
add it.
how
Okay.
come this one and this one as this part? Because I
Okay.
have.
What I suggest, why don't you go point by point? 0 plus 0 plus 0 gives you 0. So you want to get this.
Yeah.
没法直接解了。
Okay.
Yeah.
Take this little point. This value plus 0 plus 0 is this way. So until you get here, everything is the same.
Yeah.
Here.
But after that.
So after this point, you have slightly more than 8. Here you have slightly less than 0. This minus this will give you 8.
简便的方式就找。
And
Also, is
Yes.
so is this one minus this one and minus this one
yes,
to get this one.
that's right.
Oh, okay.
Okay.
Thanks.
Guys, I ask you to free every third row. Okay? Otherwise, we have a problem getting close to you if you have questions. That's all. Okay, so yeah, that one doesn't count. So you could free this one. Unless you are working together, in that case we can talk to you all. Otherwise, could you please move somewhere else? And you guys as well. Yeah, third row.
you decided to.
Right. So you can now work on problems from set 1 and set 2. And we are here to help you with any questions you might have. You know, I simply don't have time to look for a solution. We will see. You come when you can. You have to tell Marian when. No, can you again send me the list of weeks you are not available?
It's not
Okay. Okay, so you may be still available. Okay. I know, I was too busy and maybe too lazy.
so
to
I
find
found
it.
whether
Yes, yes, but we'll have to report to them when you are not. I will see. If we get too busy, yeah, I'll have to find someone instead of you. Okay. So let's. Okay, some of you are asking about the past transform tables. They are on Moodle. Lecture notes and the bottom of the lecture notes part, you will find a past transform table. So I put them a few days